Hello. Today I want to talk about refraction. So refraction is when light bends when it moves from one medium into another. And it happens all the time. Refraction happens all the time. This is the basic idea here on this slide. You can see here that what we've got is some, here we see parallel light rays entering in. They're coming from, looks like air, and into some water. And we see that they just bend at the surface there. If we had a point source, then what we can learn from that is that a light ray traveling straight in, notice this is perpendicular to the boundary between the media. If it's traveling straight in, it just proceeds through without getting bent, and how much it gets bent depends on the angle that it arrives at that interface at. Now, you've seen refraction elsewhere in your life. It happens all around us. If you have eyeglasses or contact lenses, then those work by bending the light on its way to your eyeball. They're compensating for the way that the lens in your own eye is bending the light either too much or too little. But I can demonstrate this pretty well too. Here I have a cup of water and a pencil, and you can see that this is a standard straight pencil, blue, straight. If I put it in here, what do we see? Well, it looks a little bit discontinuous at that boundary, doesn't it? What we should be seeing, yep, there we go. We can see it a little bit better there. We can see that it does look a little bit discontinuous at the top of the water. It looks like it almost breaks a little bit. Now, of course, my pencil is just straight. It's just regular. It's not a broken pencil. But when I stick it in here, the light rays are bending differently as they move through the water than just through the air. Now, it turns out that happens with a flat surface, but it can happen even more with a round surface. You've certainly seen this. That's a pretty good angle right there. There we go. That's a good angle. What do we notice? Well, we see that it's magnified, right? Inside the water, it definitely looks a little bit bigger. Outside the water, it looks a little bit smaller. It also doesn't look like it's really a straight line anymore. So again, we do see light bending on its way through the glass. Now, that may be unintentional, as the case of my pencil in a glass of water. But of course, this is a magnifying glass, and it works the same way. It makes an image. It works by forming an image, and the way it forms an image is by bending light as it passes through this magnifying glass. So here, there you go. That's pretty good. You can see an image of my eyeball, and notice it's much bigger. So that's kind of interesting. Okay, so the mathematics of this are not too bad. Here we see Snell's law. So Snell's law is what governs how much light bends Snell's law is what describes, I should say, how much light bends when it moves from one medium into another. And so here we see an image of light moving into a medium with a higher n. So here we see medium 2, here we see medium 1. This says assume n2 is greater than n1, so we have n1 here, n2 here, n2 greater than n1. And so we do see this bending, this light ray bending, as it heads into the medium. Notice that Snell's law compares the angle that it is in one medium with the angle in another medium. And I warned you about this in the last lecture in this chapter. We need to be sure that we're measuring angles with respect to the normal. And so the normal here is, of course, perpendicular to the surface. And so we want to be measuring our angle right here. It's an easy mistake to make is to measure it right here instead. Okay. So if we see light coming from a low end medium into a higher end medium, we do see it bending towards the normal. And if we see it going from a high end to a low end, we see it bending away from the normal. So notice that this is symmetrical. 1 and 2 don't necessarily mean coming from 1 and into 2, or from 2 and into 1, or anything like that. N1 and N2, that's just two different mediums. And we see that math reflected in the reality, in that the path that the light takes if it goes into the medium is identical to the path that it takes if it's leaving the medium. Okay, so here are some typical n values. You don't need to memorize any of these. In vacuum, n is exactly equal to 1. And recall that the index of refraction is a ratio, right? Recall that the index of refraction is the speed of light in a vacuum divided by the speed of light in that substance. And so recall that we always get a number greater than 1 because light always slows down when it enters a medium other than the vacuum. So in the vacuum, we get n equals 1 exactly. Air, we say 1.003, but if we're doing problems in this chapter, in the book, we can just use 1. Water, 1.33, ethyl alcohol. Moving along, notice they're getting a little bit higher. Right here, diamond has a very, very high index of refraction in the visible spectrum. And this is what makes diamonds so sparkly. It turns out that the light, the way that the diamond is cut, is kind of like this. And so it turns out that the light enters here and enters here, and it tends to bounce around and then come back out in a way that we'll describe here in a minute. This inside here, this is called total internal reflection. That's a topic I'll come to in the next video. But the fact is, we just get very large amounts of bending of light when the light enters the diamond, and it makes it so that it's more likely to bounce out. That high index of refraction makes it so it's likely to bounce out, which makes it sparkly. And it looks kind of colorful because when light bends, it spreads out into that rainbow. And anyone that's ever seen the cover to Pink Floyd's album, Dark Side of the Moon, knows about prisms and the spreading out of light into a rainbow from white light into the rainbow. Anyway, okay. Here is a quick example. A laser beam is passing from medium 1 to medium 2. It is refracted as shown. What's true? Okay. Why don't you pause the video and see if you can't figure it out. Okay, so I've drawn myself a picture here, and we've got our light ray traveling from N1 into N2. Let's draw our normal, and let's remember that we always measure angles with respect to the normal. And so looking at our equation over here, we see that theta 2 is bigger than theta 1. If theta 2 is bigger, then N2 must be smaller. And so we reach the conclusion that N2 is smaller than N1. Let's see if PowerPoint agrees. Indeed, PowerPoint does agree. Now notice we can also sort of put this into the category of memorized fact if we wanted to. I think it's easier to look at the equation. But notice that here we have when light moves from a higher n to lower n, the light ray bends away from the normal. So what I mean by that is if we move from a higher n to a lower n, the light ray bends away from the normal. In other words, our angle gets larger. Now the opposite is true also. When light moves from a lower n to a higher n, the light ray bends towards the normal. And again, we can see that in this image here. Here we see a light ray moving from low n to high n, it bends towards the normal. Here we see it moving from high n to low n, and it bends away from the normal. Okay, so in general, our problem-solving strategy here is to draw a ray diagram. And so that's a little bit of a tricky thing sometimes because we're kind of back to a section of the book where you just got to draw a picture. I mean, you have to draw these pictures. Like with finding the image from the plane mirror in the last lecture, that is the logic, is drawing these ray diagrams. And you're going to have a hard time wrapping your brain around it without that drawing. We always want to draw this line normal to the boundary. And so that's this line that I've drawn here. Right? Because that's where we measure our angles with respect to. It's very common to make the mistake of measuring them here. We don't do that. We measure them here. And then we'll show the ray bending in the correct direction. And again, here we see this is, again, this sort of memorized fact. The angle is larger on the side with smaller index of refraction, and the angle is smaller on the side with the larger index of refraction. And be careful, we're measuring our angles from normal, and then we use Snell's law to calculate what we're looking for. Okay, let's do a quick example. What is the index of refraction of the plastic if a ray is refracted as shown in the figure? Well, why don't you go ahead and give it a shot, see how far you can make it, and then you can jump back in with the video if you get stuck, or just to check your work if you don't get stuck. Okay, so here's our basic drawing, and again, the problem does ask us to find N in this plastic. So let's proceed with our steps. The first thing we want to do is we want to draw our picture. We did that. Now we should draw our normal line. What does our normal line look like? Well, right here. And we see here that we have been given the wrong angles for Snell's law. So we need to be a little bit careful. Let's go ahead and write the correct angles in here. That is 45 degrees. And this right here is 35 degrees. Okay, and now what we can do is we can just look at Snell's law and see if we can analyze from there. All right, so we are looking for N2. We could label this N1, and we could label this N2. So, in that case, we just solve for N2, and we get N2 equals N1 sine theta 1 over sine theta 2. And we can plug in our numbers. N1 is 1. And then we run our calculator, and we get an answer which is 1.23. Let's evaluate. Does that make sense? It does. It's greater than 1. That's good. Happy about that. It is a reasonable value. Also happy about that. We're right in here. Seems plausible.